So hello, everyone. I'm very happy to welcome I'm very happy to welcome Ciarán Lee here today. He heads the Causal Inference Research Lab at Spotify, while also being an Honorary Associate Professor at UCL. And so he's done really great work in the last 2 years on research in the theory of causal inference, but also like the applications and how large-scale web platforms can actually sort of apply that stuff really. And like his research has appeared in really great venues like NeurIPS and Nature and like AAAI and all of these things, and many news outlets have also sort of picked up all of the work that he's been doing. So I'm very happy to welcome him here and to hear more about the work. And the floor is yours, Ciarán.
Great, thanks very much, Olivier. If anybody has any questions during the talk as well, feel free to like raise your hand or ask me during that as well, and I'll do my best to answer those questions. So as Olivier said, my name is Ciarán. I lead the Causal Inference Research Lab at Spotify. We kind of work on a range of problems, but mainly focusing on using tools from causal inference, combining them up with machine learning and trying to solve kind of problems that we're facing at Spotify, to help our teams and also Spotify creators make more actionable decisions. So in the kind of presentation today, I'll give an overview of some recent work, but I'm going to start with a motivating example, like why should we care about causal inference? What issues might we run into if we don't use the tools of causal inference to try and make decisions and so forth? So here is a tweet that was sent out during the pandemic. So this is a researcher who was looking at the National Office of Statistics data in the UK based on the vaccination rates and the mortality rates of individuals who received a COVID vaccination and those who didn't and so forth. And he found something that seemed, at least at first blush, to be quite strange. So the orange line here is the mortality rate for those who received vaccinations. The blue line is the mortality rate for those who did not receive a vaccination. And you see that the mortality rate for those who were vaccinated against COVID is actually higher than it is for those who weren't vaccinated. So this seems strange, right? We have these randomized control trials that showed us that the vaccines reduced transmission of COVID, which one would think reduced mortality rate and so forth. But it seemed, using this observational data that was readily available from the Office of National Statistics, that the exact opposite was true. So what was going on here? So this is super strange, fly in the face of kind of medical knowledge, but it was irrefutable. It seemed, based on this clear data, that vaccines weren't really reducing mortality rates. So the question is, do vaccines work? So it turned out that this is a perfect example of what's known as Simpson's paradox. So here, what was just plotted was, the mortality rate among those who've been vaccinated and those who weren't vaccinated. But when we think about the data generation process here, the average unvaccinated person is much younger than the average vaccinated person. And this was just an artifact of the rollout strategy of the vaccines at this point in the UK, which was that older people were offered the vaccine first because it was believed they were more at risk. And so of those who were unvaccinated, it's more likely that they were younger in age than those who were vaccinated and so forth. So just by virtue of the fact that they're younger, they have a lower mortality rate anyway. So any benefit from the vaccines is somehow swamped by the increase in mortality with age. So, to use some of the lingo of causal inference, age in this context is a confounder between vaccine status and mortality. It both influences whether you receive a vaccine in the first place and also influences, your expected mortality rate and so forth. And so that biasing the data that we're kind of seeing. So it's unclear whether change in mortality is due to vaccination or due to age or some other kind of factor that we actually haven't included in these plots. Turns out that when you bucket age, when you control for it and so forth, you see that the associations we had in the previous slide flip. So the orange line goes under the blue line, which is as we would expect from randomized control trials. Vaccines work once you control for the effects of age and so forth. So what's the kind of main takeaway from this example? Kind of shows us that any action or policy change, such as the types and the ways in which we would release vaccines to the public and so forth, based on these correlations that we're seeing, would not have increased patient survival. So the main take home here is that if we rely on correlations extracted from observational data, it can lead to embarrassing, costly, and perhaps in this case dangerous mistakes. And to overcome this, we really need to understand cause and effect, not just correlation. So why is this important for Spotify? Well, how do we first of all, learn about cause and effect in an industrial setting? Well, Usually we use randomized control trials, like in the vaccine context, or we use A/B tests in large tech companies to tell us about, cause and effect. But lots of the time, we can't do A/B tests. They could be too damaging to the user experience, could be technically too hard to implement, right? If we want to figure out if app crashes cause churn, we'd have to randomize some people into a group where their apps automatically crash, and we feel like that would annoy them so much that it's not worth doing that test. If we wanted to understand whether, let's say, podcast or audiobook consumption cause retention, again, we need to randomize some users into a version of the app without those pieces of content, which again, because they knew prior to this that they existed, that would damage their user experience, and so we can't really run such A/B tests. Another great example from kind of physics is if we want to understand whether it's the moon causing the tides to change on Earth, or the changing of the tides causes the moon to orbit the Earth. We can't kind of go out and move the moon around and see what the effect on the tide is. It's just too complex a kind of problem in order for us to do a controlled experiment of. But luckily, causal inference provides a set of methods and tools for learning about cause and effect, even when we can't do an A/B test. So given some assumptions, we can then start to reason about cause and effect. So it kind of allows us to make these really actionable decisions. And so sometimes even when we can do A/B tests, they usually have kind of limitations in terms of the length of time that those A/B tests can last for, due to cost considerations and various other things. And this makes learning kind of longer term causal effects challenging in practice. For instance, if we as a tech company are interested in understanding the impact of deploying a new feature on long-term retention, but we can only run an A/B test for maybe 2 weeks or a month, then we don't know really what the effect will be in a year. If economists want to understand whether a job training program that lasts for a few weeks will lead to higher employment rates over the next 5 years, it's hard to kind of ascertain whether short-term experiments really generalize to this longer timescale and so forth. But can we use the tools of causal inference to try and answer this problem, right? So if we run a small A/B test, but we have lots of other, let's say, observational or bias data available to us, can we make claims about the longer term effects, and can we then use that to make better decisions going forward? So this is the kind of first problem I maybe want to chat about today, this short to long term kind of prediction problem. So here's a kind of more formal statement of that problem. So here's causal structure. So this is called a directed acyclic graph. It's kind of shortened to be described as a DAG. And it really, the nodes in this DAG are all about the variables that we can intervene on. So we can do an experiment that changes these values. The arrows are just meant to indicate what causes what. So the tail of the arrow is the cause, the head of the arrow is the effect. And we could just write down what we believe are the variables that have a causal impact here, which variables impact what, and so forth. So that's what a DAG really is. So we can summarize the whole problem that I've described from short to long term using this graphical notation. And then formally speaking, what we have in this problem is we're given experimental samples between variables X and variables M. So, we can intervene, change X, and see in an experiment how M changes as a consequence. But we also have available to us perhaps historical observational samples between X, M, and Y. And so Y is a longer term outcome. So it could be that X and M exist on timescales of perhaps 2 weeks. Whereas Y exists on the timescale of a year. So we can have data from the past year, but we have both X, M, and Y available to us. But when we do a new experiment, we only have access to experimental samples from X and M. So I can give a more concrete example here that describes what's going on. So X here could be dosage of a specific drug. M could be the severity of symptoms after 2 weeks, and Y could be the symptom severity after 6 months. So if we have historical observations from X, M, and Y, and we're given samples from a recent experiment about dosage and symptoms 2 weeks later, the question is, can we now combine all the biased data, which we know from the first example I gave in the talk today could lead to incorrect causal estimates? Can we combine that with the actual A/B test, which tells us the correct causal answer, but on a shorter time scale, in order to learn the proper causal effect from X all the way to Y as mediated through M? So the kind of issue here is that, as we saw in that first example about vaccinations and mortality rates, that there are confounders present that bias our data, and issues arise when those confounders are hidden from us. So we're not actually able to find out what they are and control for them. We don't have the data available to us. But because the experimental samples are from experiments, right? They're from randomized control trials. Because we're randomizing into different cells, preclude any influence from confounders, right? We literally just break the association between any confounder and treatment assignment, and we just set the treatment values randomly according to our experimental setup and so forth. So in the first set of experimental samples, the confounding isn't there. The confounding is there in the longer term samples that are drawn from observational distributions of X, M, and Y. So this is the problem that we have now. We have actual causal estimates, but now in the bigger sample, we have these confounding effects that we cannot control for because the confounders are hidden from us. And so the question is, how do we use the experimental samples to debias the longer term observational data and get some idea what the long-term causal effect would be, even though we haven't run the long-term experiment? Okay, so let's set things up slightly more formally in this context. So if we assume like a linear Gaussian model here, so I've drawn in these kind of coefficients here for each of the arrows, and they correspond to the equations on the left. So here, X is just some coefficient D times the value of W, which is the hidden confounder in our case, plus some random Gaussian noise. M is then some coefficient C times X and some coefficient times the confounder W plus some random Gaussian noise and so forth. So we can really think of a variable as being a function of the other variables that cause it in this context, plus some sort of random noise and so forth. So this is the kind of setup that we have. And what we have available to us, if I go back one slide, is we have the actual causal effect from X to M in this context, which when we look at the equations is just this coefficient C here. So it's for a unit change in X, how does M change if we hold everything else constant? So that's what C is. C is the causal effect. So we have that, and we have samples from X, M, and Y. And now we want to somehow combine these two things together to learn both. Well, we have the causal effect on M, but we want to learn causal effect then from M to Y, because then we can combine these two things to get the causal effect from X to Y. So that's the general setup. So if we take a step back for a second and we try and solve a simpler problem to get some sort of intuition for how this might work, we drop the arrow from the hidden confounder to the mediator M. So we remove that, right? So there's no now bias between M and W that doesn't go through X in this context. So this is called the front door causal structure. It was studied by Judea Pearl, who's one of the kind of founders of causal inference, in his seminal work on causality. So here it's kind of easier to figure out what's going on. The general approach to solving this, to understanding the causal effect from X to Y, is first to just, regress M on X. There's no confounder between X and M. And so the regression problem is literally just the causal problem. It tells us what the causal effect is. We can just get C from that. Now the next step is if we regress Y on M and X, any confounding between M and Y goes through X. So I can draw an arrow from M back to X, up to W, then down to Y. So there is confounding, but I've observed X, right? It's something available to me. So if I control for X, I block any confounding between M and Y. And so that's why I regress Y on both M and X, because that controls for X and the confounding. I then from that can pick up the effect between M and Y, which is A, multiply those two things together to get the causal effect from X to Y. So that's the general treatment of this front door criterion, which is like our setup, but just without this arrow from the hidden confounder to M. But actually, there's a slightly different take on this that we can make in a linear causal model. So here, I can first of all regress M on X as I did before, but now instead of just looking for that coefficient C, I look at the residual after doing this. So that random noise term that was in the structural equations. What's interesting is because this random noise term here is N sub X is independent of everything else. It's the residual. It doesn't depend on anything else in our model. You can treat it in some sense as an instrumental variable for what's going on here. Sorry, this is the one here, not NX, NM. It's the M somehow is composed of adding some times X to this residual N sub M. And so because it's independent, it acts as what's called an instrumental variable. So it's some exogenous fluctuation in our data. And because there's no now confounding between it and Y, I can use it to ascertain by understanding how NM changes, how that causes M to change, and then any resulting change in Y, I can then understand how that kind of process occurs and then figure out what A is from that. So it turns out I can reformulate the problem. Instead of doing the standard approach, I can do some regression, look at residuals and use those as an instrumental variable. And the important point is that the instrument is independent of everything else, especially this confounder W. And so everything kind of progresses as usual. So now if we add this arrow back in to get back to our initial problem, to kind of figure out what's going on here, that approach doesn't really work, mainly because if I regress M on X, because W causes M, the residual after doing M regress on X is not just this noise term here. It's some weird combination of that noise term together with the confounder W up here. And so by virtue of that, it's not independent of the confounder because it depends on it. So we can't use that directly as an instrumental variable like we did in the context when there wasn't an arrow from W to M. But it turns out that if you know what C is, which is what we get from the experimental sample, or that causal effect between X and M, which is a short-term causal effect, we can use that to debias this residual in a very specific way. So given this kind of formula here on the left-hand side, I can construct a valid instrument by first getting the residual after regressing M on X, and then adding some correction term to that depends on C. Once I do that, I get back to having an actual instrumental variable, and I can then just apply that to understand what A is here in this context. Once I have A, because I have C, I can just multiply them together to get the long-term causal effect of what's going on in this case. So it's a kind of nice generalization of that observation from that front door case. We add in this extra term to debias the kind of hidden confounding. What's cool is that we never have to observe the confounding to remove this bias. As long as we have the causal effect between X and M, we can just get this, which is kind of nice. So that's the kind of approach to how we do it there. Again, it really relies on having a linear causal model, so it could break in more nonlinear ones. We've done some simulations in kind of, higher order models that are kind of like linear combinations of polynomial terms, and you can prove that it still works, but it requires many, many samples. So it's not overly reliant on the linearity assumption, but it does need some aspect of it to kind of work. So we did some experiments on kind of by creating like a synthetic example out of some real world data. So we looked at this data set called the International Stroke Trial. So it's a large randomized trial of up to 14 days of a specific type of therapy after stroke onset. And it also has a longer term observations of, people who weren't in the randomized control trial, but like had this treatment anyway. What were their symptoms after 6 months, after a year, and so forth. So we did some sort of messing around with this data where we added in some synthetic outputs correlated in the right way to satisfy our assumptions. We used systolic blood pressure at randomization as the treatment, age as the unobserved confounder, so we didn't give that to our models. And the goal is to estimate the effect of a synthetic mediator that we constructed ourselves on the synthetic outcome. Again, we did this synthetic construction so that we know what the right answer is, but yet we're still using real data, so we get a sense of the proper variance of all these things and how good our estimators are relative to variance consistent in real data. So on the right, we kind of have some results at different kind of levels of noise added to our data. So the solid line is our method, and the dashed line is the kind of method that doesn't have the ability to correct for this unobserved confounding. You can see the different colors are different noise levels, different standard deviations, and so forth. But for all of them, our method reduces bias, which is kind of nice to see. So again, it's limited by the fact that we need this additivity assumption, but it seems to still work even when, as in this case, additivity is likely broken in various cases. So it does reduce bias, which is cool. So we had this paper, it was accepted at the CLEAR conference, so that's the Causal Learning and Reasoning conference, the nice venue for causal inference papers. We had a blog on the Spotify research webpage, which is kind of nice. If you're interested, you can check those out. But the main thing I want to discuss now, so we've discussed, how you can solve this kind of clear applied problem of, we can only do experiments for a short time. We want to figure out what the longer term consequences are, so we can, do this in a way that's free from bias, given certain assumptions. But there's different types of causal questions we can ask beyond just saying, okay, what would happen if I took this action today, if I did this intervention, if I gave this treatment. So Pearl has a nice way to formalize the kind of different types of causal questions one could ask. So he's broken these out into a hierarchy of 3 levels. So the first is about just standard observation. It's kind of where traditional machine learning lives. The next is about acting or intervening on the world. Again, it's where the randomized control trials would live, and it's kind of been the topic of what we've spoken about thus far. But the third level is what he calls counterfactuals, or the ability to imagine different scenarios and act in those imagined scenarios and so forth. And actually, this top layer has some very interesting properties when it comes to making decisions that are relevant for kind of big tech companies like ours. So we'll go through these a little bit more detail just to explain them, and then I'll discuss the main question I want to try and answer in the rest of today's talk. So the first one is this observation one. So if we think about this classic setup of whether smoking causes lung cancer, the kind of traditional discourse of this that arose in the 50s was, well, there is a correlation between smoking and lung cancer, sure, but this in principle could be due to some unobserved genetic factor that perhaps predisposes someone to crave nicotine and also develop these types of sicknesses and so forth. So in principle, just by looking at correlations, we can't tell the difference between whether smoking actually has a causal effect or whether all of that causal effect is due to some unobserved genetic factor or hidden confounder. So at the observational level, all we're doing is talking about conditional distributions. Whereas when we go to the next level, which is about intervening, we're at the level of kind of randomized control trials where we can kind of reach in and force somebody to smoke if they don't smoke, and we can see that then decouples any influence from any potential underlying genetic predisposition, right? Because it's not due to that precondition that they're smoking, it's because we were forcing them to smoke, or they've been randomized into the arm of the trial that is requiring them to smoke and so forth. And so this is what breaks the connection between correlation and causation and allows us to assess whether smoking is actually causing cancer. So Pearl came up with a nice notation for how to describe and write down mathematically the difference between standard observational distributions and what he's calling interventional distributions, so distributions that arise after an intervention or treatment is applied. And so this subscript on the C is meant to kind of tell us that we've reached in, forced smoking to be true, regardless of any precondition like genetics or other confounders. And in that context, I want to figure out what the probability that cancer is true is here. So that's what that subscript means there, S equal to T. We've intervened and we've forced. So now we're kind of brought to the top layer of this kind of causal hierarchy, which Pearl refers to as this counterfactual layer. So here we get something slightly confusing, at least at first blush. So we want to ask the following question. So given the subject is a smoker and they have cancer, what is the chance they wouldn't if they hadn't smoked in the first place? So now we're kind of mixing up 2 different types of kind of information. We've observed that they both smoke and have cancer, but we want to say counter to that fact, had they in fact not smoked, so smoking had been false, what's the probability that cancer would have been false? So it's really trying to figure out, right, can we disentangle any genetic factors from smoking and figure out, okay, which one has actually led to having this kind of illness for this specific individual. And it's written in a weird way. So this conditional distribution looks strange, right? Because C and S appear on both sides of the conditional symbol. So on the right-hand side, we have, the observation, the factual information. So C is equal to true, S is equal to true. Then the left-hand side, we want to ask, okay, given that context, now, had we intervened, so had we in the subscript forced smoking to be false, we want to ask, what's the probability that cancer would have been false in that context? So that's the kind of general description of what that means in a conceptual level, but you might be asking, how on earth could you ever compute that quantity, right? It seems like a very strange thing to even write down. So Pearl came up with a kind of 3-step procedure to do this that he showed to be sound and complete, given some basics of kind of, structural logic and counterfactual logic and so forth. So the first step to computing that weird quantity at the top is to do what he called abduction. So given the factual information, which is, about smoking and cancer, I want to condition on that and update my knowledge of what the distribution over the hidden confounders might be in this context. We might have a prior for this. We don't know what it is exactly, but we could have some level of uncertainty over it. But given this factual information, it updates our knowledge, right? Perhaps if they smoke and they have cancer, maybe it's more likely they have certain types of genes that predispose such things in the first place, and so we can do some Bayesian updation there. The next step is we do this action step. So we do the intervention where we force now smoking to be false. And now in this new model where we've done this intervention, right, we've broken the connection between the hidden confounding and smoking. We now use this new abducted prior over the hidden confounder. We sample from that, and we sample from the value we've set for smoking, and then we look at what the probability that subject has cancer is. So it's just three-step procedure, and it kind of makes sense of how we would compute these things. So here's a kind of quick, concrete example that's meant to kind of illustrate this process. So here we have a causal structure relating certain types of symptoms, so shortness of breath and chest pain, to certain diseases, so arrhythmia, certain infection, diabetes, etc., to a risk factor, so being overweight and so forth. So here we have a structure. We want to ask, what's the probability that given I've observed certain symptoms, that those symptoms would have reduced had I been able to, let's say, cure a very specific disease, right? So the first step, as we say, is we've observed shortness of breath and chest pain. So that's the first step. So given that observation, we do some abduction. We update our information about all the other variables and how likely or not likely they are given this observed information. The next step is we do these actions. We reach into our model and we set a certain disease to be off or to be cured in this context. And then given this context, given the updated priors over everything, given that we've done this action, we now do prediction. So we sample forward for everything and we see, okay, does that change the original observation? So does it reduce the likelihood of shortness of breath and chest pain? In this case, it does. What's interesting is that we could distinguish these two cases by saying, okay, what would have happened had instead we intervened on diabetes? Would the distribution over the shortness of breath and chest pain have changed? And in this case, that's not possible because there's no causal arrow from diabetes to shortness of breath and chest pain. So this counterfactual thing lets us, understand a little bit about what possible diseases could be causing these symptoms in the first place, and so on. So that kind of like is a hint as to what these counterfactual objects might be good for in terms of decision making, right? You could, reasonably say, well, okay, if randomized controlled trials live at level 2 in Pearl's hierarchy, why do we need counterfactuals, right? Like all the information that we usually use to make decisions comes from these trials, comes from A/B tests. So why would we need to go to level 3 at all, right? Why is it interesting? Why is it useful in the real world context? So I'm going to now try and convince you that it is useful by providing an example from medical diagnosis. So as a kind of setup to this problem, we can consider like a disease model, which is a generalization of the example I just showed about counterfactual inference. So we have, a 3-layer model. We have symptoms, we have diseases, we have risk factors, we have the causal relationships between all of these. The causal links here are in this specific disease model have been put in by medical professionals, so doctors and epidemiologists and so forth, and the kind of probabilities for each of these kind of links and the priors for all of these kind of things have also been extracted from both data at the general population level as well as expert information from epidemiologists and doctors and so forth, and the likelihood of certain diseases occurring in the population and kind of so forth. So we have this big model. And the question is, okay, now we have this cool model, can we use it to try and help diagnose people if they come in and say, okay, I have these symptoms, what then is the most likely disease in this context? So this is a kind of old problem that's been studied since the 80s. And the standard approach is just to use posterior ranking to try and get a sense of what the disease that's most likely explanation of the symptoms is. So it kind of would ask the problem, okay, given we know certain symptoms exist, right? Maybe we have a chatbot that asks the patient, what symptoms they're expressing. So we observe that. We now want to ask, okay, what's the most likely disease given that observation? So we do some Bayesian updating and figure out what the most likely diseases are under that. Then we just rank them and then output perhaps the top one or something like this. So what I want to propose instead of that is to use a counterfactual probability instead of just standard Bayesian updating. So it's a different type of question. So saying, given the symptoms are present, would they not be had a specific disease been cured? So you can go through all diseases and see if that's the case. And then if one disease would increase the likelihood that the symptoms would go away if it had been cured, then that's your diagnosis. And in some sense, when you talk to doctors, this is more in line with how they do diagnosis than this kind of Bayesian updating approach. They kind of think about, okay, well, if I gave the patient a treatment for that disease, would these symptoms go away? And if so, then okay, that's the disease causing the symptoms. And so I can then do that kind of treatment based on that. So why might this work? So here's a kind of thing that was kind of hinted at in the last example. So if I just used posterior ranking here, so if I asked for the probability that a certain disease should be present given the observations, in this context, that posterior ranking model would output diabetes as the top as the top explanation. Why? Well, if I have shortness of breath, then it's likely that I belong to the part of the population that is overweight. And again, if I belong to that population with some high probability, it's likely that I maybe belong to a subset of the population that has type 2 diabetes. And so now there's this correlation between diabetes and shortness of breath, but there's no causal link between them. So if I were to say, okay, diabetes is the most likely disease given this evidence, well, it's only likely because there's this confounder, which is overweight between these two things. So if I were to recommend that as the diagnosis, I would have kind of resulted in a bad diagnosis, because if I intervened with insulin, I wouldn't reduce my symptoms. Whereas if I ask a counterfactual probability, right, given I've observed these symptoms, look at which diseases are likely, now if I turned off a disease, oh, look, I reduced the likelihood of these symptoms, it's likely then that that disease is a good diagnosis or a good explanation of why these symptoms are present, and then I can do the treatment on that disease to reduce the symptoms. So that's the kind of basic idea, or the intuition at least. So how did we test this? Right, we got about 1,700 medical cases prepared by an independent panel of doctors. So they look kind of like this. There was some evidence, there was some background on the patient, and then there were as a kind of proposed disease proposed by this panel of doctors that was the most likely, or the, you know, what they would have considered the correct explanation in that case. These kind of vignettes are given to, you know, GPs when they're training to become general practitioners. They have to pass a test with all these types of things. So it's very similar to the kind of tests that GPs generally do. So given all these, we want to figure out what the disease is, and the disease in these cases just this given one at the very top, which is hidden from the model. Okay, so what happened when we compared what our model did, so the counterfactual one, versus what the standard posterior ranking did relative to a separate collection of 44 doctors. So these doctors weren't involved in creating these cases. They were shown them and asked, okay, given all this information, which disease do you think is underlying what's going on here? And so when we compare our model to the kind of correlational one, we place in the top 25% of doctors. So, you know, we're better than 75% of the doctors in this 44 doctor cohort, whereas the standard approach is only better than about 52% or something like this. So, you know, it's still good, but it's about on par with the average doctor, whereas we're much higher in terms of what a doctor can do. If you had just done the kind of standard approach using interventions, you would be somewhere in the middle of these two. We did that experiment, but it's not on this slide here. So what this is showing is that counterfactuals are offering improved decision-making beyond level 1, which is observations, and beyond level 2, which is just interventions. So this is based on a paper we had in Nature Communications a couple of years ago. We got a bit of press, a new scientist for this, which was exciting. It's more aligned with how doctors try and make these decisions in the kind of real world. But the main question you might have here is that all of this is contingent on a fixed disease model, which was available to us because we worked at a healthcare startup, and it had been created by this healthcare startup. And we were given this structure, right? All these parameterizations, all these probabilities, all these links already. And so the question you might have is, okay, so counterfactual inference seems useful, but how do we apply it in the real world to real messy data when we don't have such already built models such as the one we had here? And so that's the kind of next problem I want to briefly discuss in the last kind of few minutes. So here's another motivating example just to kind of illustrate the type of thing that we're trying to do here. So in the developing world, diarrheal diseases are kind of leading cause of disease and mortality and so forth. And to reduce some of these in certain parts of Western Kenya, a local NGO built protective cement structures around randomly selected groups of springs. So usually where they get their water, there could be bacteria, could lead to diarrhea and kind of have bad consequences. So the NGO decided, okay, if we put concrete around where the water was coming out, perhaps that would prevent the disease and bacteria from getting into it in the first place. And researchers from an action lab based, I think, in the US, worked with this NGO to estimate the average treatment effect of this intervention. So that's at level 2 of Pearl's hierarchy. So doing a randomized control trial where they had, a group of candidate springs to do this intervention on, build this concrete, and they randomly selected a subset to do it on, randomly selected a subset not to do it on, and compared the kind of difference in diarrhea of those two things. They found that it reduces diarrhea in children under 3 by about 25%. So right, it seems great, right, that this definitely has an effect. And so the next question is, should this intervention be scaled up, right? Should all springs have this concrete kind of put around them? But it's expensive to do this, right? To invest in this way, and so beforehand, one should really be really certain that the intervention that is going to be implemented is having the desired consequence, and it wasn't something else. So for instance, when people from the NGO came into an area that started building the concrete around the spring, they were educating the people who live there about what they were doing, why they were doing it, and so forth. And so people were now understanding, oh, there's bacteria in the water. Maybe we should be more careful with how it's consumed and so forth. And so in principle, the intervention had these knock-on effects, and it's unclear whether it was the intervention itself or these knock-on effects that was actually having the desired consequence, right? If it's just about education, it's much cheaper to do that than it is to build all these springs. So we'd want to understand which one is the right thing we should do to get the desired outcome in the kind of most efficient way. So the real question that we want to answer is, how likely is it that the negative outcome, right, getting diarrhea and having mortality, was caused by exposure to diarrhea and not to something else? So we want to answer, given a child developed diarrhea after drinking from an unprotected spring, would they have developed it if they drank from a protected spring, right? So that's the question we want to answer. But that's a counterfactual question. We've observed factual information that they, got diarrhea after drinking from an unprotected spring. We want to ask, counter to that fact, updating our knowledge about the type of individual that they're likely to be, given that information, would they still have developed it if they drank from a different spring, so a protected one? So the real question we want to ask is what's called the probability of necessity in the literature. So it looks like this specific counterfactual question here in the box. So given that they drank from an unprotected spring and they got diarrhea, if we had intervened to make them drink from a protected spring, what's the likelihood they wouldn't have gotten diarrhea? So that's the thing we want to answer, but how do we do that from data if we don't have a model, right? We needed a model in the previous example. So the way we kind of do this is by having a slight change in how we compute counterfactuals. So Pearl himself, who came up with the first abduction action prediction approach to doing counterfactuals, also came up with a different way of doing it that are kind of logically equivalent, but conceptually is slightly different. So what he did was, the first step is to take your original causal model and just duplicate it, just copy it, and then draw links between everything. But now we call the original model the factual world, and we call the duplicated model the counterfactual world. And the reason why hidden variables and confounders are duplicated, the arrows coming out of them between factual and counterfactual, is that they're hidden, so they're outside of our model. And so we want to make sure that the factual and the counterfactual world are as close as possible. But now in the counterfactual world, we can do an intervention. We can drop arrows, we can set variables to certain kind of quantities. And now in this context, the counterfactual probability is not just this weird nested thing that involves the same variables on both sides of the conditioning symbol, but it's actually standard Bayesian inference, but on this larger network. So I want to ask, okay, in the counterfactual world, what outcome would I have gotten given an observation in the factual world? So it's just reducing counterfactual inference to standard Bayesian inference in this case. What's cool about this is that this graphical structure actually tells us the types of neural network architecture we could build to estimate these counterfactual questions just using standard kind of machine learning in this context. No need for fancy updating and action and all this kind of stuff. So we take our original causal model, we create the twin network, which is just duplicating it and reducing arrows based on the interventions we care about. And what we do is we just create a neural network whose architecture just copies that structure straight away. And it turns out that by training this in a specific way, and just by asking standard questions between the two outcome heads, we can estimate these counterfactual probabilities, which is cool. So I'll kind of skip a little bit the technical details of how this training is kind of done. But the basic idea is the graphical structure enables us to kind of have a simple blueprint for a neural network that will answer these questions. We can also do nice things in training this network by imposing additional regularization constraints that enforce things called identifiability constraints, which make sure we're learning the right thing and so forth. But doing all this, you might be wondering, okay, well, what's the answer? It looks like you can do it now. It's possible. You can use machine learning to learn these counterfactual quantities when you use the correct neural network architecture. So now what's the answer? Does this intervention work or does it not work? And it turned out that the probability of necessity is quite small. So what that shows us in this context was that children would have likely still developed diarrhea even if the springs had been protected. And so it's telling us that, okay, something else is actually helping children in this context. It's not necessarily about putting the concrete around the springs and so forth. So we needed to kind of think a little bit more around how one would do this intervention to get the desired output. But it's showing us an example where understanding things at the second level, so just the average causal effect, isn't fully sufficient for really getting a good decision in this context. We needed to understand the counterfactual level, which is what counterfactual inference is kind of all about. So this basic approach of using twin networks and so forth to estimate these counterfactual probabilities from just observational data, we published in this paper here on the left. We got some nice feedback on Twitter from Judea Pearl himself, who's this grandfather of kind of causal inference. So he introduced twin networks in, I think, 1995 or something like this. It was a very small paper with like toy examples, and there was nothing about, machine learning or anything in there. But what's cool is he said that, he was wrong in dismissing twin networks after certain types of assumptions had been imposed. He said our work showed that, twin networks are really computational instruments, and they're useful in kind of making these types of decisions and explanations and so forth, which is kind of nice to see. So you might be kind of wondering, that all sounds good, but it's got nothing to do with Spotify. So what types of decisions are you using counterfactual inference to help with in Spotify? Well, one thing that we're doing at the moment is trying to decide on, who should receive a promotion. So how we should kind of define this is which users need to be shown a promotion in order to engage the content. We don't want to send a promotion to users perhaps who would find the content organically anyway. It's like a waste of a promotion. Plus, it might annoy them to get loads of promotions in a certain time period. So we really want to be selective in who receives these things, really only target those who will engage the content if and only if they're shown the promotion. So not showing them will lead to not engaging, showing them will lead to engaging. But importantly, this makes sure we don't target those who would engage even if not shown a promotion. And even more than that, it makes sure we don't target those who just will never view a promotion or hate promotions so much that they would have found the content organically and enjoyed it on their own. But the fact that they're shown a promotion of it annoys them so much that they're just not going to kind of connect with it. It's a very small case, but it's still kind of, a possibility. So here, this corresponds to a specific counterfactual distribution, which is the joint probability that a user doesn't engage if they're not shown a promotion, but they do engage if they are shown a promotion. So this is, again, a counterfactual distribution we can estimate with these twin networks. Again, you can talk about other things like, given that they enjoyed a specific piece of content, they engage with it, what's the likelihood they would have engaged with something else had you shown them at that instant and so forth. And this kind of helps in making these decisions on who should be served for these types of promotions and so forth. We got some press in this paper as well, which is nice. So MIT Tech Review overviewed our paper, have a nice title there, but even stranger was Bill Gates somehow came across this article and shared it with his Facebook network, which somebody messaged to me and showed me, which was very strange. So any efforts on my part to engage Bill Gates in funding a causal inference institute have so far fell on deaf ears, but I'm still working on it. See how it goes. In the last 2 minutes, I just kind of want to give a brief overview of the power of these deep twin networks and why it kind of helps us in making even more complex decisions. So the great thing now is we get to use all the tools of deep learning and so forth to estimate these counterfactual distributions and causal effects. And so here's an example with quite high dimensional data. So trying to answer counterfactual questions about images. So here we're looking at a specific medical image. So it's a cardiac ultrasound. And we want to answer the question, what would this specific image look like if a patient had a different certain aspect of their heart called the kind of ejection fraction? So we're given an image and conditioned on that, we want to figure out, okay, what would it look like had this one thing been slightly changed or this description of the image been slightly changed? And again, we can just input this into a arguably big and complex, but still a deep twin network. We just have more layers and, we use contrastive stuff and et cetera, et cetera. This is kind of overview in the paper in the top right. But here is a kind of, let's see, this is always a danger. So you can see here the images or the videos that were generated from this query. So the one on the left is the actual image. So that's the ejection fraction of 45%. Then we have two images. They're mislabeled here, but they're effectively just saying, okay, conditioned on what that image, on what that video looks like, we want to see what it would have looked like had we slightly changed those ejection fractions and so forth. And you can kind of see, okay, the one with the bigger ejection fraction has that bigger thing. The one with the lower has smaller than the actual thing, and everything else looks anatomically similar to the original image and so forth. So it seems like it can work, which is exciting. So on that kind of last note, showing the power of the kind of deep twin networks and combining both deep learning and causal inference, I'm going to kind of end. So let me go on to the last. So it's going to have a great time re-showing this video. And then we can go on to the final. Let's see. The final slide, which is this one here. So overall, you using causal inference to answer questions is kind of vital. Otherwise, we can run into issues with biased data and making incorrect, possibly dangerous decisions. There's still loads and loads of problems that remain to be solved to really apply the causal toolkit to real-world problems. And there's loads of applications we've been working on at Spotify that I can't speak too much about yet. But if you're interested, I'd love to chat more about this or just causal inference in general. So thanks for your attention. And that is the end of my talk.